Hi guys, this is Professor Darwish with you, and today we are going to talk about Euclidean algorithm. It is used for computing the greatest common divisor between two integers, abbreviated as GCD. This method has been around for a while. It goes back to ancient Greek, and it was created by ancient Greek mathematician Euclid, almost like 2300 years ago, 300 BC. The idea behind the GCD is that you are giving two integers and you are supposed to find the common largest divisor integer between them, and it is positive. Of course, we're looking for the positive number or positive integer that divides both a and b. There is one of the characteristics of the GCD. There is one of the properties. If the two numbers are zeros, GCD of 0, 0 is basically 0. So 0 and 0, the common divisor is basically 0. Another actually definition, so we can say that this is here a definition. Okay, so we can define the GCD between two integers a and b is to find the maximum integer, which is a positive integer in this case, k, and this has to be positive, of course, this positive integer, such that k divides a. So this symbol here is divide a. Means that divides a without any remainder is 0, and k also divides b. Okay, so the common between them, which is k in this case, will become the greatest common divisor. It has to be the maximum number. Okay. Now, there is another property that is also going to be very important and essential. So this is here the property. I'm going to run a video on it, a separate video. It's when the GCD between two integers a and b is equal to 1, specifically 1, which is obviously that those numbers, okay, so the largest common divisor between them is 1, is basically we can state that a and b are relatively prime. So because the only common divisor between them is 1, and that's the largest, so basically they are relatively prime. So this is we are going to use this feature in cryptography, and specifically in different classical as well as modern ciphering techniques. So actually it's used in a fine cipher, okay, and usually it is used if you have a cipher code and you are going to decipher it, you will be utilizing this important property. So I'm going to show you this in a later video. Now let's take this example. You are supposed to find the greatest common divisor between, for example, 7 and 15. Both are integers, so this is integer a and this is b. Now, I mean, in a simple way, before we get into the algorithm itself, let's take a look at number 7 here. So number 7, let's find the factorization, or what are the factors that 7 is made of. So basically, what the numbers that 7 can divide by. So we'll find that is of course with the remainder 0. So we'll start with 1, and is 7 divisible by 1? Yes. Answer 7, and the remainder 0. Now you continue to 2, 3, 4, 5, 6, 7. When we divide by 2 is actually going to give us fractions, so it's not divisible, and in this case it's going to be divisible by 1 and itself. Interesting. So this number here, when it's divisible by itself or 1, we call it prime. So this is actually a prime number. Okay. Now let's take a look at the 15. So 15, as we said, that is divisible by itself by 1 and by itself. So these are the numbers. We were looking for the set of numbers or the set of integers. Now, is it divisible by 2? No, because there is a remainder. Is it divisible by 3? Yes. 15 by 3 is 5, and the remainder is 0, so 3 is there. And obviously 4, no, and then 5, 6, 7, 8. Of course, this here is 15. 6, 7, 8, 9, 10, 11, 12, 13, and 15. So this is actually the set of factors which is related to 15. And if you are looking here for the GCD between this, and let me change the color here to green, and when you look at the largest one, so it is 1. So 1 is the common. Okay, there's nothing in common here except the 1, and it happened to be 1. And in this case, we can say that 7 and 15, they are going to be relatively prime. Okay, so and this is going, again, the application of that, I'm going to demonstrate it in a later video. But when 1 is the only factor that is common between them, and this is the largest one, so we can say that 7 and 15 are considered to be relatively prime. Now we'll start working on the Euclidean algorithm itself. So let me change back to the white marker. Right, so and let's take a look at the algorithm here. So I'm on the other side here. I'm going to run the algorithm. I'm going actually to start with an example and try to show you the algorithm here. So find, this is another example. Of course, you know, this example is on the algorithm itself. Find the GCD of the two numbers 254, comma 100. So I have chosen two numbers, and find the greatest common divisor, which is, let's call it D. Now we are going to use now the Euclidean algorithm. In using Euclidean algorithm, so we are going to denote the largest as A. So this is the largest number here. So this is going to be A, and this is going to be B. We are going to transform this into linear equations. So we are going to write or express the largest integer, which is A, in terms of B. Okay, and basically in this case, you know, here A is equal to B, and of course if B divides A, basically then we'll have a quotient here, so there will be a Q. So let's call it here Q1. Now obviously there will be also a remainder R1. So A can be expressed using this equation. So this is a linear equation, and of course, you know, if I substitute here, maybe so to clarify my point. So A is 254, so let's substitute 254 equal, and this is the remainder, I'm sorry, the quotient Q, and for the quotient we are going to look for the number. So let me put a box here, and B is 100. Of course, this is multiplication, plus R1, we want to find the remainder. Now, of course, here, if you want to express this one as a linear equation, looking for the quotient, so actually we divide, basically you divide A by B. So 254 divided by 100, it is 2, it's not 1. Okay, it is not 3, because 3 times 100 is 300, so it is actually 2. Okay, so the quotient has to be an integer. Okay, so it is 2 times 100 is 200. So what's the remainder? So we will find out that the remainder is 54. Now notice that there is a rule here, okay, which is R1 is greater or equal to 0. It has to be greater or equal to 0. Of course, if it's equal to 0, that's it. It's done. It's divisible. So A divides B, or actually B divides A, and with certain number. But for R1, this is R1 and has to be less than B in this case. So you obviously notice that the number is 54, and 54 meets that condition, obviously. So because if it's 100, then this number will change to 3. So in this case, this is what we call it the first pass. Let's call this one the first pass. Basically, we want to run this in several passes. So this is the first pass, or the first iteration. Now, this is what is the structure for this one. Now, the algorithm itself says, okay, we need to move, and there is something actually I need to mention here. This position here, A, it's called the dividend. Okay, so this position is now the dividend, and of course B in this case is the divisor. Okay, or this one is the divisor, and R is the remainder, and of course Q is the quotient. I think EINT, quotient. So those are like some terminologies, because actually we can express them in a table if we want to, but this is we'll come back to that later on. So again, A, or when the number in this side, we call it the dividend. This is the quotient, Q, and B is the divisor, because here we divided A by B, and quotient is the result, and the remainder is R1. Okay, so again, let me just remove them, so not to make it I don't want to make it so crowded, but at least those, the terminology that we use. Okay, so now this is, again, as I said, this is the first pass. Now the algorithm says, okay, let's move the divisor, okay, which is in this case B. We'll move B in the position of A, which is the dividend, and we move the remainder in the position of B. So basically it's like shifting to the left, but what we shift the B in the place of A, and R1 in place of the B. So how is gonna look like in the second pass? It's gonna look like this. The equation is gonna look like, so we have 100. Okay, so 100 actually, and there will be a number here, and 54 plus another remainder. So if I want to express it in terms of letters, so 100 is actually, now it is B equal to Q1. In this case, we finished Q1, this is now Q2, and this is R1 plus R2. Now the condition is, now R2 is greater or equal to 0 or less, or not. There is no, let me delete this one, and it has to be less than the number 54, which is in this case R1. So let's take a look. Let's try to solve those numbers. So 100 divided by 54, is it 2? No, it will be 108, so it is actually 1, so we can put 1 here. So what is the remainder? So this is 1 times 54 is 54, so obviously the remainder is 46. So the remainder is 46, and this is what we call it the second pass. or the second iteration. So we will continue, because our criteria here is to look at this one. This one has to reach we have to reach the 0 for R2. For us to stop the iteration, R2 has to reach 0. So now let's do the shifting again. So we'll shift this here and here. This is, and we'll have the third pass. So we'll have again. So let me write it as an equation. So we'll have R1 is equal to Q3, and here is R2 plus R3. Substitute the numbers. So we have 54 is equal to R2 is 46, and let's put box here and box for R3. As you know, R3, the condition is greater or equal to 0 and less than 46, which is in this case R2. So the number that is applicable here is 1 times 46, because 54 when we divide by 46. So as you can see, it is not 1, it's not 2, it is obviously 1 times 46. What's the remainder? The remainder is obviously 8. 8 is our remainder. So now here we finished pass number third pass. So then we do the shifting again for the R2, and then R3 in place of R2. So we have here, in terms of equation, we'll have R2 is equal to Q4 R3 plus R4. Obviously R4 is greater or equal to 0 and less than R3. So let's put the numbers. R2 is 46 and R3 is 8, and we put a box here so we can find that number plus the remainder. So when divide 46 by 8, it is 5. If we put 6, it will be 48, so it should be less. So it is 5. 5 times 8 is 40, and the remainder is 6. So this is the fourth pass, and again we need to continue because this number is not 0 yet. Okay, so I'm continuing now to the fifth pass. So again I need to put here R3. So R3 will go in place of R2, and R4 will come here. This is Q5 plus R5. Of course, the condition R5 greater or equal to 0 and less than R4. Again, we just erase this one here. Now if I substitute the number R3, it was 8, so I put 8 here, and we put a box instead of Q5. R4 was 6 plus another box for R5. So when we divide 8 by 6, it is 1, and the remainder is 2. Again, the remainder for R5 in this case is not equal to 0, so we cannot stop. So this is the fifth pass or iteration. So again we do the shifting one more time, and again this is going to be R4 is equal to Q6 R5 plus R6. So, and the condition for R6 is greater or equal to 0 and less than R5. So let's find the substitution here. So we move 6 here is equal to a box, and R5 is equal to 2 plus another box. So which 6 divided by 2 is actually 3, and obviously here 3 times 2 is 6, and the remainder is 0 in this case. So R6, we say that it's greater or equal to 0 and less than 5. If it is 0, we stop. Let me change the color. So here we stop, and we found already our greatest common divisor. So I'm going to change the color back to the red, and this is actually this is the 6th pass, and this is the last one. And actually this is where, of course, we stop right there. There's no more. We reach 0. So the condition here is to reach 0. Now when we reach 0, the greatest common divisor between the 254 and 100 is equal to this R5, which is the previous remainder. So it's actually equal to 2. And this is the method of finding the greatest common divisor using Euclidean algorithm. So this is the Euclidean algorithm, guys, and we found that 2 is the greatest common divisor. All right, so I'm going to run different examples in different session, and for now, thank you and have a good day.